Just after midnight, the ground under a small desert city in Southern California started moving, and it did not stop. 17 earthquakes in the first hour, then more. Within 2 days, that number climbed past 350 separate quakes, all clustered in the same few square miles, all shaking the same stretch of farmland that sits almost exactly between two of the most dangerous fault systems in North America. This is not a hypothetical. This happened. It is still being studied right now, and the location matters more than almost any other earthquake swarm in the last decade, because of exactly where it sits on the map. Today we are breaking down precisely what happened, why this particular patch of desert has scientists paying closer attention than usual, what a brand new study says about the stress sitting underneath it, and what would actually happen if the thing everyone quietly worries about finally lets go. No exaggeration, no doomsday theater, just the seismology, the history, and the honest math behind the risk. Stay with me on this one, because by the end, you will understand why a cluster of small, mostly forgettable earthquakes in a farming town most people have never heard of is being watched by seismologists from Pasadena to Menlo Park like it might be the opening paragraph of a much bigger story. Let's start with exactly where this happened, because location is everything in this story. The town is Brawley in Imperial County, sitting in the desert south of the Salton Sea and north of the Mexican border. It is not a place most people could point to on a map. It has a population of around 25,000 people, and it sits on farmland fed by the Colorado River. But underneath that farmland is one of the strangest and most closely watched patches of crust in the entire state of California. Geologists call it the Brawley Seismic Zone, and it functions as a kind of tectonic hinge. To the south of it runs the Imperial Fault, a fast-moving, well-behaved strike-slip fault that has produced damaging earthquakes before. To the north of it, the Brawley Seismic Zone connects directly into the southern tip of the San Andreas Fault, the single most studied and most feared fault line in the United States. In plain terms, Brawley sits in the gap that links the two systems together, a step-over zone where stress transfers from one fault to the other. When something rattles down there, seismologists do not just check the local damage reports. They check whether that rattling could nudge the San Andreas itself. So here's what actually happened. In the early hours of the swarm, the earthquakes came fast, one after another, most of them small, in the magnitude 2 and 3 range, the kind of shaking that rattles dishes and wakes people up, but does not knock anything off the walls. Within the first hour, more than a dozen quakes had already been logged by the United States Geological Survey. As the morning wore on, the swarm kept building instead of fading, and it eventually produced a magnitude 4.7 earthquake just after midnight, centered a few kilometers west-southwest of Brawley, at a depth of about 14 kilometers. That one was strong enough to trigger the ShakeAlert earthquake early warning system, sending automated alerts through the MyShake app to phones across Southern California seconds before the shaking reached them. It was felt as far away as Palm Springs, more than 100 kilometers to the northwest. It even reached San Diego, nearly 150 kilometers away. By the time the most active phase of the swarm had run its course, the United States Geological Survey had logged close to 400 separate earthquakes in that same tight cluster, with roughly a dozen of them strong enough to be felt directly by residents. An estimated 180,000 people experienced light to moderate shaking over the course of the sequence. No major injuries, no structural collapses. But also, and this is the important part, no clear ending either, because a swarm does not behave the way a normal earthquake does. And that difference is exactly why this event deserves a closer look than most people are giving it. This is a good moment to pause and actually explain what a swarm is, because the word gets thrown around loosely, and understanding the difference changes how you should interpret everything that follows. A normal earthquake sequence has a clear shape. There is a main shock, one dominant event that releases the bulk of the stored energy, followed by a decaying tail of aftershocks that get smaller and less frequent over time, following a predictable mathematical pattern that seismologists have studied for over a century. You know when the big one happened. Everything after it is just the fault settling down. A swarm is different, and in some ways more unsettling precisely because it breaks that pattern. In a swarm, there's no single dominant event. Earthquakes of similar size cluster together over hours, days, sometimes weeks, without a clear peak and without a predictable decay curve. Seismologists at the USGS have been blunt about this distinction when discussing the Brawley activity specifically, explaining that swarms do not necessarily decay the way an aftershock sequence is expected to. The activity can ramp up, quiet down, and then ramp up again, sometimes over a span of weeks before it finally settles. That unpredictability is precisely why this particular patch of ground gets so much attention every single time it wakes up. And it has woken up before, more than once, which gives scientists an unusually rich history to compare this event against. The Brawley Seismic Zone has produced notable swarms going back decades. In 1981, The Westmoreland swarm produced an earthquake of magnitude 5.8. In 2012, a swarm centered almost exactly where this one occurred produced a magnitude 5.4 earthquake. Smaller swarms have popped up repeatedly in the years since, including significant activity in 2020 that pushed the United States Geological Survey to issue a formal short-term forecast, estimating at the time a 1 in 300 chance of a magnitude 7 or larger earthquake following within 7 days, and a 10% chance of a somewhat smaller but still significant earthquake up to magnitude 6.9. Those numbers sound dramatic, taken out of context, but they need to be read correctly. A 1 in 300 chance is still overwhelmingly likely to not happen. The far more probable outcome, in the 90% range, has always been that the swarm simply decays and life returns to normal within about a week, which is exactly what has happened in the vast majority of past cases. But the fact that the USGS bothers to run and publish that calculation every single time tells you something important. This is not treated as a routine background hum. It is treated as a legitimate, if low probability, warning sign, precisely because of what sits just to the north of it. Now, here's a question worth sitting with for a second before we go any further. Why does a swarm of mostly small earthquakes in a farming town generate this level of scientific attention when California experiences small earthquakes literally every single day? The honest answer comes down to mechanism, and this is where the science actually gets interesting. Most of the seismic activity happening under Brawley is not driven by the same slow tectonic grinding that produces earthquakes along the main trace of the San Andreas. It is driven substantially by geothermal processes. The Brawley Seismic Zone sits directly above one of the most productive geothermal fields in the country, where extremely hot fluids move through cracks in the crust at depth, some of it naturally occurring, some of it tied to geothermal energy production in the area. When those fluids move, they do two things simultaneously. They change the pressure acting on nearby faults, and they can literally lubricate the rock surfaces, making it easier for small sections of fault to slip past each other. Seismologists studying the region, including Dr. Lucy Jones, one of the most recognized earthquake scientists in California, have described this as essentially a normal process for this specific stretch of ground, something the zone does periodically as fluids redistribute at depth. That explanation is genuinely reassuring on its own. It means most of what is happening under Brawley right now is the crust doing something it has done many times before, in a location built almost specifically for this kind of behavior. But reassuring is not the same as irrelevant. And this is exactly where the story widens out from a local curiosity into something with statewide implications. Even though the swarm itself is largely a local, geothermally driven phenomenon, it is happening inside a fault system that a major new scientific study says is under more stress right now than at any point in the past 1,000 years. That study, led by researchers including Dr. Lillian Burkhart and published through rigorous peer review earlier this year, built a physics-based computer model simulating a full millennium of earthquake history along the southern San Andreas and the neighboring San Jacinto Fault. The team fed the model radiocarbon-dated sediment records, tree ring evidence of past ground ruptures, and historical seismic observations stretching back centuries, then ran the simulation forward to today to estimate how much stress has accumulated along each fault segment. Their conclusion was about as direct as scientific papers get. Stress on multiple segments of the San Andreas and San Jacinto fault systems is now at or above the highest values recorded anywhere in that 1,000-year simulation, not approaching a threshold. According to the model, already past it. To understand why that finding matters so much, it helps to actually walk through how a fault stores energy in the first place, because this is not intuitive if you have never had it explained properly. Picture 2, enormous slabs of crust grinding past each other deep underground, which is essentially what the Pacific Plate and the North American Plate are doing along the length of the San Andreas Fault. Deep down below about 10 or 15 kilometers, the rock is hot enough and under enough pressure that it can actually flow and creep past itself relatively smoothly, almost like thick tar shifting slowly over time. But closer to the surface, in the upper crust, the rock is cooler, more rigid, and it locks together through friction instead of sliding. The plates underneath keep moving at their steady pace of a few centimeters a year, but the locked section on top cannot move with them. Instead of releasing that motion as gradual, harmless creep, the locked section absorbs it as stored elastic strain, essentially bending and compressing the surrounding rock the way you might bend a stiff wooden plank. Except this bending happens over years, decades, sometimes centuries, completely invisibly, with nothing at the surface hinting at what is building up below. This is the same mechanism called elastic rebound that seismologists have understood since the early 1900s, and it is the reason a fault that looks completely calm on the surface can be sitting on an enormous reserve of stored energy underneath. The southern section of the San Andreas Fault has been locked in exactly this way for an unusually long time. The last major rupture along that southern stretch was the Fort Tejon earthquake of 1857, an event estimated at roughly magnitude 7.9. That was 169 years ago. For all of that time, the Pacific Plate and the North American Plate have continued grinding past each other along this fault at a rate of roughly 5 centimeters a year. And because the fault has not slipped in a major way during that entire span, essentially all of that motion has gone into stored stress rather than released motion. That is the physical basis behind the Burckhardt team's finding. It is not a prediction pulled from thin air. It is a direct calculation of how much energy has been quietly accumulating in the rock for nearly 17 decades without a major release valve opening. And then the study adds a second finding that makes the picture noticeably more complicated and honestly more concerning than a simple single fault story. The San Andreas and the San Jacinto fault systems physically intersect at a location called Cajon Pass, roughly 50 miles northeast of downtown Los Angeles, a spot most people only know because Interstate 15 runs directly through it on the way to Las Vegas. Researchers found that this junction can behave as what they are calling an earthquake gate. Under the right stress conditions, a rupture that starts on the San Andreas Fault can potentially jump through this junction and continue onto the San Jacinto Fault, turning what might have been a contained single-fault earthquake into a combined multi-fault rupture. According to the study, a joint rupture crossing through Cajon Pass could produce an earthquake somewhere between magnitude 7.4 and 7.8. And instead of threatening a corridor along just one fault line, it would simultaneously threaten the Los Angeles Basin, San Bernardino, Riverside County, and the Coachella Valley all at once. The researchers found that stress levels on both fault systems right now are running close enough to each other and elevated enough in absolute terms that this earthquake gate is effectively sitting unlocked. One of the study's co-authors, USGS geologist Kate Scherer, put the underlying logic plainly, pointing out that because it has been such a long time since either fault system has ruptured, the accumulated stress on both of them is simply enormous. Another seismologist involved in the broader research effort, Ahmed Elbana of the University of Southern California, was asked directly when the next major event along this system might arrive. And his answer captures the honest uncertainty at the heart of all of this. It could be today, tomorrow, in 10 years, or in 30 years. On a geological timescale, there is functionally no meaningful difference between those possibilities. Now, before you assume that this Brawley swarm and that headline stress study are describing the exact same phenomenon, it is worth being precise because good science depends on precision, and this is where a lot of casual coverage gets sloppy. The swarm activity under Brawley is happening in the Brawley Seismic Zone specifically, a geothermally active stepover region. It is not technically occurring directly on the main trace of either the San Andreas or the San Jacinto Fault. Seismologists have been careful to note that swarms in this particular area tend to run roughly perpendicular to those two major fault lines, rather than directly along them, which is itself an interesting structural detail, suggesting there may be additional connecting structure linking the two systems that scientists are still working to fully map. So this is not a case of the San Andreas itself suddenly rupturing. It is a case of activity occurring extremely close to the southern terminus of a fault system that an independent, peer-reviewed study says is more heavily loaded with stress than it has been in a millennium. Experts monitoring the swarm have acknowledged that there is a non-zero chance that activity in the Brawley zone could transfer stress onto the San Andreas itself and trigger something larger there. But they have consistently described that chance as low, based on how the swarm has actually behaved, decaying in intensity rather than building toward a dramatic single event. Before we go further into what scientists are actually watching for next, take a second and drop a comment, letting me know if you have ever felt an earthquake, especially if you live anywhere near a fault line like this one. I read through these every time, and it genuinely helps to hear what the shaking actually felt like from people who have experienced it firsthand rather than just from a seismograph reading. And if this kind of deep dive into what is actually happening beneath the surface is useful to you, hitting subscribe means you will not miss it the next time one of these systems lights up. Because based on the pattern we are about to walk through, this will not be the last time this year that we are talking about Southern California's fault network. This Brawley swarm also did not happen in isolation, and looking at the broader pattern across California over the same stretch of time tells its own story. In the same general period, Southern California experienced a swarm of activity starting near Indio, beginning with a magnitude 4.9 earthquake that triggered more than 250 aftershocks along the San Andreas system in the Coachella Valley, an area that includes Palm Springs and the Inland Empire. Up in the Bay Area, the San Ramon Valley, sitting on a different but equally significant fault network involving the Hayward and Calaveras faults, experienced a swarm of 33 separate earthquakes within a 90-minute window in a single morning, ranging up to magnitude 4.2, strong enough to knock items off shelves in local businesses. Weeks later, the same region produced another cluster event, with the largest measuring magnitude 4.2 once again. And separately, in the same broader window that the Burckhardt stress study was published, Southern California recorded a cluster of earthquakes within a 36-hour span, including a magnitude 4.3 near Kern County and a magnitude 4.1 near Fraser Park, both occurring on smaller structures adjacent to, though not directly on, the San Andreas and San Jacinto systems the study identified as critically loaded. None of these individual events are catastrophic. None of them, on their own, would normally justify this level of attention. But taken together, they paint a picture of a fault network across California that has been unusually active across multiple geologically distinct locations within the same calendar year, sitting on top of a fault system that independent research says is holding more stored stress than it has in 1,000 years. So here is the honest, myth-busting section. Because this is exactly the point in the story where online commentary tends to run wildly ahead of the actual science, and it is worth correcting that directly. Does a swarm near Brawley mean the so-called big one is imminent? No, and seismologists have been consistent and clear on this point every single time this question comes up. Earthquakes cannot currently be predicted with any precision, not by swarms, not by animal behavior, not by any signal scientists currently have access to. What seismologists can do, and what studies like the Burckhardt research actually provide, is a probability estimate, a statement about elevated risk over a defined window of time, not a countdown clock. When the United States Geological Survey calculates something like a 1 in 300 chance of a large earthquake following a swarm within 7 days, that number is doing real scientific work, but it is also telling you, quite directly, that the overwhelmingly likely outcome remains that nothing catastrophic follows. Dr. Lucy Jones, who has spent decades studying exactly this region, has repeatedly pointed out that this kind of swarm activity is common behavior for this specific zone, not a departure from normal. The honest scientific position sits in the middle ground between two extremes. It is not nothing, because the underlying fault system genuinely is under record levels of stress according to peer-reviewed research, and every major earthquake in California's history had to start somewhere, on some ordinary day, with some ordinary sequence of smaller events preceding it. But it is also not a countdown. The probability of any specific swarm being the trigger for the big one remains low, even while the long-term background risk for the region as a whole continues to climb the longer these fault segments stay locked. This is also a good place to talk about what the actual monitoring infrastructure looks like right now, because California is not simply watching and hoping. Since 2019, the ShakeAlert Earthquake Early Warning System, built and operated through the United States Geological Survey in partnership with the state of California, has been fully operational across the West Coast. The system works on a genuinely elegant scientific principle. When a fault ruptures, it generates two distinct types of seismic waves. The first to arrive are called P waves, which travel fastest but carry relatively little destructive energy. Behind them come S waves, which travel slower but carry the violent shaking that actually causes damage. ShakeAlert's network of more than 1,500 sensor stations, a network that as of last year was reported to be roughly 95% complete across the state, with the remaining stations in less populated areas scheduled to come online by the end of this year, is built specifically to detect that first wave of P waves the instant a rupture begins, calculate the likely magnitude and location within seconds, and push out an alert before the more damaging shaking arrives. During the Brawley Swarm's strongest event, that exact system activated automatically, sending alerts through the MyShake app to phones across the region before the shaking reached them. That is not a hypothetical safety feature. That is a system working exactly as designed, in real time, during an actual live event. What that early warning buys people is not much time in absolute terms, but it is far from nothing. 10 seconds of warning is enough to drop and take cover under a sturdy piece of furniture, which protects against the leading cause of earthquake injury, which is falling debris, not structural collapse. It is enough time for a surgeon mid-procedure to pause. It is enough time for a train to begin automatic braking before crossing a bridge. It is enough time for elevators to stop at the nearest floor and open their doors instead of trapping people between floors. It is enough time for someone driving on a freeway to ease off the accelerator and move toward the shoulder rather than being caught mid-maneuver. None of this prevents an earthquake from happening. All of it meaningfully reduces how much harm that earthquake causes once it starts, which is precisely the lesson seismologists have drawn from comparing outcomes in well-prepared regions against outcomes in regions without this kind of infrastructure. The geology of an earthquake is fixed by physics the moment a fault ruptures. The human cost of that earthquake is determined by decisions made long before it ever happens. So what exactly are scientists watching for next? Now that the most intense phase of the Brawley swarm has passed and activity has largely settled back down, the first thing is simply continuation and pattern. seismic networks are tracking whether the swarm stays quiet, flares back up, as swarms in this specific zone have historically done more than once, sometimes reactivating weeks after appearing to end. Second, researchers are watching for any migration of activity, meaning whether the location of the earthquakes shifts northward toward the San Andreas itself or southward toward the Imperial Fault, because a shifting pattern would suggest stress is actively transferring between structures rather than staying contained within the geothermal zone where it started. Third, and this is where the modern monitoring network really earns its keep, scientists are watching continuous GPS stations planted across the region, instruments sensitive enough to detect ground movement on the scale of millimeters, looking for any sign of aseismic creep, meaning sections of fault slowly slipping without producing detectable earthquakes at all, which can sometimes precede or accompany periods of swarm activity. Satellite radar interferometry, a technique that can measure ground deformation across wide areas from orbit, is being used in parallel to check whether the surface above the Brawley Seismic Zone has shifted in ways consistent with fluid movement at depth versus tectonic slip. And fourth, in the broader context of the Burckhardt stress study, researchers are continuing to refine their model of the Cajon Pass earthquake gate, trying to better understand exactly what conditions would be required for a rupture to actually jump from the San Andreas onto the San Jacinto Fault, because that detail single-handedly determines whether a future major earthquake in this region stays contained to one fault or becomes the much larger multi-fault event the study warns is now a realistic possibility rather than a remote worst case. Let's talk practically for a moment, because information without action is really just anxiety, and that is not the point of any of this. If you live anywhere near an active fault system, whether that's Southern California, the Bay Area, or frankly any seismically active region anywhere in the world, there are concrete things within your control, regardless of what any individual swarm ends up doing. Download an earthquake early warning app if one is available in your region, because those precious seconds of notice genuinely change outcomes. Know where your gas shutoff valve is located, since gas line ruptures are a leading cause of post-earthquake fires. Secure heavy furniture and top-heavy items to the wall, since falling objects, not collapsing buildings, cause the majority of earthquake injuries in developed regions with modern building codes. Keep a basic emergency kit on hand with water, food, a flashlight, and any necessary medications sufficient for at least 72 hours, since infrastructure and emergency services can be stretched thin in the immediate aftermath of a major event. And have an actual communication plan with your family for a scenario where phone networks are overloaded or down entirely, because that was one of the most consistently reported failure points during earthquakes in regions without robust preparation. None of this takes more than an afternoon to set up, and all of it is precisely the kind of decision, made calmly, well before any shaking starts, that determines whether a major earthquake becomes a manageable emergency or a genuine catastrophe. Zoom all the way out for a second, because this is really the core lesson sitting underneath everything we have just walked through. The San Andreas Fault and the San Jacinto Fault have been doing this exact thing, locking, storing stress, and eventually releasing it for millions of years, long before there were cities, highways, or freeway interchanges sitting on top of them. Nothing about the Brawley swarm changes the fundamental physics of that system. The fault will rupture again someday, the way it has ruptured dozens of times across geological history, because that is simply what strike-slip boundaries between tectonic plates do. What has changed, and what genuinely matters here, is what has been built on top of that fault system in the century and a half since it last ruptured on its southern stretch. Millions of people now live directly along or near this fault network, and the honest, unglamorous truth that every seismologist working on this research would tell you directly is that the raw geological hazard is not really the story worth losing sleep over, because that hazard has been constant for millions of years and will remain constant regardless of what anyone does. The actual story, the one that determines whether the next major earthquake here looks like a controlled survival emergency or something dramatically worse, is entirely about preparation, building codes, early warning infrastructure, and individual readiness, all of which remain firmly within human control even when the earthquake itself is not. The Brawley swarm has largely quieted for now, at least by the standards of its opening days, but the fault system it sits beside has not gone anywhere, and neither has the stress calculated to be sitting inside it at levels unseen in 1,000 years. Scientists will keep watching the GPS stations, keep checking the satellite deformation data, keep an eye on whether the pattern of small earthquakes shifts or migrates, and keep refining exactly how that earthquake gate at Cajon Pass behaves under real-world stress conditions, rather than just inside a computer model. None of that tells us when the next major rupture will actually happen, because nobody currently has that ability, and any claim otherwise should be treated with real skepticism. What it does tell us is that this specific stretch of Southern California deserves to be watched closely, not with panic, but with the same clear-eyed, methodical attention that turned a magnitude 7.4 earthquake in Japan into an event with only a handful of injuries instead of a mass casualty disaster. The geology writes the first half of every earthquake story. The preparation, the infrastructure, and the decisions made in the calm period beforehand write the second half, and that second half is still being written right now, in real time, by the choices being made today. If you found this useful, the thumbs up genuinely helps this reach the people who live in these exact regions and need to actually see this information. Subscribe if you want to stay ahead of the next update, because between this swarm, the ongoing stress research, and the rest of California's fault network, this is very unlikely to be the last time this story develops further. And drop your thoughts in the comments, whether you're in Southern California watching this unfold in real time, or you're somewhere else in the world wondering how prepared your own region actually is. We'll keep tracking every update as the data comes in, every shift in the swarm, every new reading off the GPS network, and every piece of research that comes out of this newly stressed, closely watched stretch of the San Andreas. Thanks for sticking with this one all the way through, and we'll see you in the next one.